Okay. Well, let me start by really congratulating the organizers of this conference. It turned out to be a very good conference, and I'm really happy to see so many young people who are interested in functional programming. That means a lot. It means that the functional knowledge is spreading very quickly. And not only in programming per se, but also I noticed that there is a lot of interest in the theory behind functional programming and the philosophy even of functional programming. So that's very interesting. I prepared a talk about more or less very similar topic, or a continuation in a sense of what Phil was talking about in his opening keynote. And I must say, we did not really coordinate this. It was like two separate people came up with the idea of talking about propositions and as types and Curry-Howard isomorphism, which for me is a sign that this might be an important topic, that like the time came to actually start talking about it and spreading this knowledge among programmers, that it might actually become very useful. And it's really mind-opening to think about that the stuff that we do, you know, doing spreadsheets and Java code and websites, that actually there is something behind it that's really fundamental and basic, that actually relates to mathematics in such a deep, very, very deep way. So there was a little bit of discussion about what does it mean? What does it mean that there is this weird similarity or isomorphism between fundamental mathematics, which is the on the one hand logic, right? Different types of logic, and programming, type theory, lambda calculus. And I'm going to add to it one more thing, and that's category theory. And I'm glad that Phil talked about Curry-Howard isomorphism so much, so that I can actually concentrate more on what my real passion is. That's the category theory. So I'll show you that actually this isomorphism is extended to not two things, but three different branches of mathematics, if we consider programming also a branch of mathematics. So there is this question, you know, first of all, why are these three independently developed theories, why are they actually converging? Why are they look sort of like three fingers that are sticking out of water, right? And we did not realize that there is actually a hand below the surface of the water, and these three fingers are just part of this hand, right? What does it mean? And then there is category theory, and the category theory is sort of the arm that extends from this hand, you know, or maybe the whole body, because category theory describes essentially all our knowledge about mathematics. It just abstracts stuff from so many branches of mathematics. You know, you can do topology in category theory, you can do measure theory, you can do logic, Banach spaces, you know? It all has this basic structure that can be abstracted into categories. Why is it? Well, so some people say, you know, this is a discovered thing, that there must be, you know, something in this universe or in multiple universes, right? In multiverse, that you can't even imagine how this can be any different. We are just digging out and discovering, a lot of mathematicians are Platonists. Plato believed that there is this absolute truth that we are just discovering. And I thought about this because this is a problem that always interests me, especially as a programmer. How do we program? We always program and invent programming languages and write our programs in a way that's composable, right? Like, this is the most important thing. Your programs have to be composable so that you can split a huge problem, chop it into smaller pieces, solve each of them separately, maybe chop these pieces into even smaller pieces, and so on. And then we have to compose the solutions to these problems into one bigger problem, one bigger program, right? So this composition is like intrinsic in programming. And if there is this commonality between programming and different branches of mathematics, and then there is this commonality between all branches of mathematics and category theory, then there must be something really deeper behind it, right? And what is common among all these things, and this is what category theory tells us, is the principle of composition, right? I'll talk about the definition of category, and you'll see that a category is really about nothing else but composition. Tells you how to compose things from smaller things. That's the essence of category theory. So if category theory describes all these other branches of mathematics, and then what is this thing that all things tend to compose? Is that like intrinsic thing about nature that things have to compose? But mathematics is not really even about nature, right? I mean, we think we are discovering something. It's more about our minds, right? We discovering, physicists discover elementary particles. They are part of this world, right? But mathematicians discover ideas, and these ideas sit in our brains. And we know why we are doing programs in a composable ways. As programmers, we understand this. That's because of the limitations of our brain. We just cannot do this stuff if we try to solve the whole problem at once. The only way we can deal with problems is by dividing them and then recombining the solutions. So composition for us is just a way for us humans with the monkey brains to deal with reality, to understand it, and to develop our theories. So developing theories about stuff is really studying how to make things understandable through the monkey brains. Okay? So the fact that we always try to split everything and then recompose the stuff is really the property of our brains. And if somebody had different kinds of brains, some other civilization in some other universe, maybe they wouldn't have this. Maybe they wouldn't have category theory. Category theory tells us that all these things are similar. Why are they similar? Because they are created for our monkey brains. There are things, as a physicist, I can tell you, that we always try to decompose things in physics. And the deeper we go, the less composable things really are. Like people thought about atoms, the ancient Greeks, atoms are these elementary things, and you compose a bunch of atoms and you get substances, And then we discovered, oh, atoms actually, they consist of electrons and protons and neutrons. Okay, then we look at protons and neutrons and say, oh, there are quarks inside, and so on. Now we are trying to understand quarks, and we are trying to understand the standard theory, and we are thinking, you know, maybe they are not really that elementary. Maybe they contain something inside, maybe the strings, maybe membranes, stuff like this. And in quantum field theory, classical mechanics is really easily decomposable. You know, we think of like things moving in space and hitting each other and so on, interacting, and we can describe the movement of each particle separately and then combine and get the whole description of the whole system, right? But in quantum mechanics, that's not really true. If we are trying to describe one particle, that's easy. But that's just one particle not interacting with anything else. The moment we get two particles, if they are far away and we can forget about their interaction, then they can be described separately. One wave function, another wave function, well, just add them, okay, and you get a sum. So that's perfectly decomposable. But you bring them together closer and closer and closer, and suddenly it's not a composition of two wave functions. It's something more complicated. It's really a wave function of a two-particle state, which is not a composition of one-particle state, and so on. The more particles you add, the more this doesn't compose, right? And this is probably why physicists are stuck right now, because they are trying to decompose stuff so that we can understand with our brains, but nature is not built like this. Nature is not by itself decomposable, and that's like a shock for us, right? So that proves once more that maybe all the stuff that we are discovering is not really about nature, it's really about our brains. That might be a little controversial statement, but I will try to prove this in a small example. So let me see, what's my next slide? It's this truth, okay? So I titled this the truth about types. It doesn't mean that I will finally uncover the truth, but that truth is easily representable in all these three branches. In logic, in type theory, and in category theory. So so true is like one particular value that describes truth, okay? And in logic, truth is defined by this introduction rule. So Philip mentioned that there are these introduction and rules that define things. And the statement that T, which is the truth, or maybe it's an upside down thingy that's opposite of false, which is this thing, right? That the truth is always true. Okay? Truth is always true. And you don't have to make any assumptions in order to show that true is true, because it's an axiom. It's by definition. So the definition of truth is through this introduction rule, which says what's above the line is our assumptions. And there is nothing above the line here, right? So no assumptions. Under no assumptions, you don't need to tell me anything. I'll guarantee that true is true. Now, the same statement, because we are talking about this Curry-Howard isomorphism, and actually I'm talking about Curry-Howard-Lambek isomorphism, and Lambek is the guy who actually found the third branch, he showed that category theory is also isomorphic to these things, some particular types of category theory. So in types, the same thing is described by saying that this type called unit type is inhabited. So that it means that there is a value, there is a particular value available from this unit type. And this is sort of Haskellish notation, in which this value is like a pair of parentheses, and the type is also a pair of parentheses. So on the left you have the value, on the right, on the left you have the value, on the right you have the type. So value unit is of type unit, okay? And that's corresponds to truth intro. Now in category theory, exactly the same intro is through the terminal object. And I'll talk about what the terminal object is. I just wanted to show you that these three things, they look so completely different, but they are different notations from different branches of our knowledge to describe the same thing. And of course, in logic, we know we have to prove things, right? So we have the proof theory. And what does it mean to prove something in logic? It means to derive it from some other principle. So you make certain assumptions, and then you use these rules of proofs to finally prove a particular proposition. So if the proposition is A, the proof is like what's above this horizontal line. So there will be a bunch of other statements above this line that's like this follows from this follows from this follows from this. Your assumptions, you discharge your assumptions, and so on. So this is a very well formalized part of proof theory. In type theory, the same statement corresponds to types are propositions, right? So we know how to prove proposition A. It means that we have a type A. By this isomorphism, there is a type A, okay, that corresponds to proposition. The proof corresponds to the fact that there is an element of this type. There is something in there, that the type is not empty. And this is the notation for this. We have some environment, gamma, which composes all our assumptions, right? And in this environment, there is an element X of type A, which means A, we proved A by pointing an element, by creating an element, or by producing an element of this type. Okay? And in production of this element, we might have evaluated some functions and so on. Now, in category theory, this fact that, so now an object in a category corresponds to a type, corresponds to a proposition, right? So an object in category theory doesn't really have any elements inside, because in category theory you never look inside objects, right? But you can also specify, that an object is sort of like non-empty if there is an arrow coming from the terminal object. The terminal object I mentioned before, I will show you the definition of what the terminal object is, but this is just to show that, this kind of very different approach to the same thing. So, let's go into category theory. So far I've been talking about certain things that, without explaining what they are. I don't know how many people here know some elements of category theory. Quite a few. Okay, good. So for the rest of you, a category is the definition of a category. Category theory is about categories. So the definition of a category is extremely simple. This is something you can explain to a toddler, essentially, to a child. Because a category is just a bunch of objects and a bunch of arrows connecting these objects. And if you ask me what an object is, it's abstract. It's nothing. We assume that there are objects. They don't have any structure. You cannot look inside an object. It's just like a dot, a point particle. There's no structure in it. So the only thing you can divine about these objects is how they connect to other objects using arrows. Okay, and this picture kind of suggests that a category is sort of like a graph whose edges are directed, with directed edges. And it's sort of true. There is a little bit more to it. I mean, it has certain conditions, but essentially it's like a graph, except that it may have infinitely many objects, and it could have infinitely many arrows between any two objects. Okay, so it could be a lot of connections between a lot of objects, or it could be just one object with one arrow, and that's also a category, right? So it covers ground from like almost, well, actually there is a category that has no elements, no objects, and so from nothing to infinity of infinities and so on. Those categories can be even larger than sets. So this is what I said, right? Nodes, and we usually call these objects, we give them some names like A, B, C, and so on, right? And the arrows between these objects are called morphisms, but people call them arrows as well. So even mathematicians will just call them arrows. You probably don't want to call them arrows in Haskell, because in Haskell there is an arrow library that has nothing to do with morphisms. So this is Haskell notation for something. Well, it's not really exactly the morphism. I'll talk about function objects, but it essentially says A is an object, B is an object, and we think of A and B really as types, because types corresponds to objects in category theory. So, I mean, for me, it's like the same thing, so I don't really distinguish these things. So I might be saying object and might be saying type, or proposition, because it's all the same, right? So we have an arrow between A and B, which we think of as functions. Okay? That's not all. They have to be certain conditions fulfilled. And this is the most important thing. This is why I say category theory is about composition, because the major things that you have to be able to do in a category is compose arrows. So if you have an arrow from A to B, you have another arrow G from B to C, then there must exist a shortcut from A to C. There must be another arrow. This arrow is called the composition of these two arrows, and it's denoted by G circle F, that's read as G after F. You can think of a function F being performed and then the result of it passed to the function G, right? Like in F sharp, you actually do it from left to right with this vertical bar greater than, right? So, it's kind of easier for a programmer to think from left to right. at least in Western cultures, right? So it always exists, a composition of two arrows if they match end to end, right? So arrow from A to B and another arrow from B to C. B has to be the same in the middle. You can always compose them and you get a new one. And this composition, we want this composition to be associative. That's another condition, right? So that we can forget about the order in which we were doing composition. Like if we compose 3 arrows, we just compose 3 arrows and not have to say, well, we first combine the first 2 arrows and then combine it with third arrow. So these little piggies correspond to objects, right? And this is the composition of these 2 arrows. A useful device to visualize these things. And final thing that we have to assume about these arrows and composition is that for every object in the category, for A, for B, for C, and so on, there is a special arrow called identity that loops. It goes from this object back to itself. And it's called identity because when you compose it with any other morphism that's composable with it, right? So like if you have identity at A is an arrow from A to A, and if you combine it like ID after F, you get F back, right? That's why it's called identity. And if you combine G with identity, you get G. Notice the different order. This is like 2 separate sub-laws of this law of identity. And this little piggy is to illustrate the fact that there might be many different looping paths from A to A, right? They are different. But at least there is at least one there that's the identity. These other paths, when you compose them with external morphisms, they won't give you back the morphism, they will give you something else, another morphism, not the same. Okay, set is a very good example of a category. And essentially, people started with thinking of sets and then they generalized them to categories. So set is a category of sets. So objects in this category are sets. What's an arrow between 2 sets? What's a morphism between 2 sets? It's a function. A mathematical function is always from one set to another set, right? So set is a category of sets and functions between these sets. Okay? There are many different types of categories. Set is like a very special kind that we sort of understand very well because we have a lot of experience with sets. But the thing is, when you look at sets through the perspective of a category, then there's one thing that you are forbidden to do. You cannot look inside the set. Okay? All you can say, oh, this set is different from that set. That's because the connections of the set, the functions, are different than the functions coming from here, right? Like this set maybe has only 1 arrow going outside, and this set has 10 arrows going outside, okay? So we can say, oh, this one is a special set because it has only 1 arrow, right? And when we describe sets in terms of these arrows, functions, right? We are not supposed to look and say, oh, this is a 3-element set. No, you cannot say that. Because that would mean that you looked inside the set. So let's start describing objects in a category with this constraint that we cannot, that objects have no structure inside. All we can say about objects is how they connect to others. And it turns out that you can define a lot of interesting objects in a category by just looking at arrows. okay? And the simplest example is initial object. Initial object, by definition, is an object in a category. If it exists, it doesn't have to exist in every category. It's an object that has arrows to every other object in this category. So this is called as a universal construction because you look at the whole universe of objects. You are describing one particular object by its property of how it connects to everything else. And that's a very powerful thing to say about an object. You say something about how it connects to everything else. And in this case, initial object is defined as an object that has one arrow to every other object. And it has to have exactly one arrow, okay? There are other objects maybe that have multiple arrows going to other objects, but this one has a single arrow going to every single object, okay? A unique arrow. That's the definition of initial object. Okay, and of course the question is, well, what's the initial object in set, right? Because that's where we get our intuitions. Well, the initial object in set, so it would have to be a set that has only one function going to every other set. And it turns out that the empty set fulfills this condition. So what's an arrow from an empty set to some other set A? Well, it's a function. Function that takes something from an element of an empty set and maps it to an element from some other set. Okay, but do you hear me? I'm saying an element of an empty set. And empty sets have no elements, right? So this is a function, yes?
How do you know if the set is empty if you're not allowed to look inside?
Well, okay, I'm just explaining what it means in terms of set theory. So like that we can identify how would we describe this set in using set theoretical language? We would call it an empty set, right? But I have defined an empty set using arrows only. I said this is an initial object. If an initial object in the category, so I have a way of pointing at this object using only its arrow properties, right? External properties. But now I'm translating it back. It's like, okay, so what is this? We know that these objects are sets. So what's a traditional description of this object, right? The traditional description of this object, it's an empty set. It has no elements, right? And in fact, you can always create a function from an empty set to any other set, and you'll never be able to call this function. So it's like a function that doesn't really do anything, but it's okay because you will never be able to call this function. Okay? So it's like in vacuum, this is true. So, and this function in Haskell, actually, this function is called absurd. And it corresponds in logic into saying ad absurdum quod libet, right? From falsehood, you can derive anything, right? It's like if pigs could fly, then something. Then I'll, and void here represents this. On the one hand, an empty set. On the other hand, it corresponds to a type void, which we know has no elements, right? It's an uninhabited type. Has no elements, okay? And this is not the same void type as we use in C or C++. We'll get to it later. Void exists in Haskell, but I don't know if it exists in any other language. Maybe in ML. Or how about F#? Is there something that has a type that has no elements? No, unit is the actual.
Void in .NET, it breaks everything.
Yeah? Okay, good to know. Okay, so in category theory, there's this like, you buy one thing from me, you'll get another thing for free. And so if you have a construction that creates a initial object, well, you get the opposite of this for free. And what's the opposite of a initial object? It's a terminal object, right? And it differs from the definition of initial object by reversing all the arrows. So if you say, oh, the beginning of this arrow is really an end of it, and the end is the beginning, right? You're kind of reversing the arrows, then whatever construction you were doing, you get a new construction. Okay? And terminal object, by construction, is this object that has incoming arrows from every object. There is a unique incoming arrow to this object. Not 2 arrows, not 3 arrows, but just unique. From every object, there is a unique arrow to this object. Okay? So it's like the opposite of the initial object. And then again, the question is, so what is it in set? Okay, so we can point it using arrows, but you might look on the other side and say, oh, I know set theory. What are you talking about in terms of set theory? In terms of set theory, I'm talking about a singleton set. A singleton set has only one element, okay? And is there a unique function from any type to a singleton? Yes, it's called, in Haskell, it's called unit. It's a function that simply ignores its argument and always returns the only element in its codomain, which is this single element of a singleton set. There are no other elements in the singleton set, it's just only one. So this function must always return this one element, right? So in Haskell, this pair of parentheses or an empty tuple is an element of, no, here it's a type, this is the unit type, and here it is an element of this type. Same symbol, but this means element, this means type, because this is a type definition, this is the definition of the function, the implementation of the function. So function unit underscore means ignore the argument. I need one argument, but I will totally ignore it. I'm not concerned about it, and I will return the unit element. So that's the terminal object in set, a singleton. Now you might say, okay, is there only one terminal object? Is there only one singleton set, or are there many singleton sets? So no matter whether you believe that there is one or many, if there are many, they are all isomorphic. Okay, so a set that contains one apple is the same as a set containing one orange. Because they are isomorphic. And you can prove it actually from this general construction that it has to be isomorphic. So, universal constructions like this, initial object, terminal object, are practically the only way of defining picking objects in a category. Because you cannot look inside the object, so you have to look how they connect to every other object. In what way? Or you can create a pattern of a few objects, a few morphisms, and say, how does this pattern relate to every other instance of this pattern in the whole category, right? That's the only way of defining things. and it's called the universal construction. And using universal construction, you can define things like products, right? We know what a product is in set. It's a Cartesian product. It's a set of pairs. One element from one set, one element from another set, make a pair, and you get a set of these pairs, and that's the product, okay? So that's the intuition there. But now in category theory, we are forbidden to pick elements, right? So what is a product then? Is there a product in category theory? And again, you use universal construction. So the universal construction for a product consists of this pattern. Well, you fix objects A and B, and you want to find an object that is the product of these two. Let's call it C, right? So the pattern is that you have an object C, and the only thing you can say about this thing is that there must be a projection, right? So there is an arrow from C to A. That corresponds to picking the first element of the pair. We know this. I can tell you in secret, right? That's picking the first element of this pair. There is another one, Q, another projection. That's in secret, the second element of this pair. But we are not supposed to talk about the contents of these objects, right? So the only thing we know that there is one morphism here and one morphism here, okay? This picture, that's our pattern. And by the way, if you translate this pattern in category theory into logic, it corresponds exactly to the two elimination rules for what's a product in logic? Conjunction, and. If A and B can be proven, then A is true. If A and B can be shown, then B is true. Right? So that corresponds to a morphism from this pair, A and B, to A. Okay? Morphism here. Morphism Q takes pair A and B and returns B. So this is the secret behind this, right? This is how we implement it actually in Haskell. But this is a type, AB. And again here, AB here's a type, here's an element. So in Haskell, people always, use, not always, but use the same letters and same symbols for types and values. You get used to it. But in the beginning, it's hard. You're reading Haskell code and you say, wait a moment, this is type, right? And this is a value. Are we passing types to a function? No, we are passing a value. And so on. But you get used to it. So this is product elimination. This is conjunction elimination, two conjunction eliminations that correspond to two arrows from this product object to these individual objects, right? But this is not good enough. There can be many objects like C with these two projections. Only one of them should be the product, right? So you can think of lots of objects. Well, not in every category, but like in set category, there's a lot of sets that have two functions. Actually, every set, you can define two functions for it to some two other objects, maybe except for the empty set. Mm. So we need more. In order to pinpoint exactly the C that corresponds to the Cartesian product in set, we have to evaluate somehow the instances of this pattern. So, like this is a query that we are giving to Google. Show me all patterns like this in your category. And you get lots and lots of hits. And you want just one. You want the top one, right? What does it mean, top one? It means that you have to have some kind of hierarchy among them. You can say, this matches my pattern better than something else. And this one is the best of all of them. And the best one will be called the product. All the others are just candidates for products. No, wannabe products. So there's the second part to universality, which is the ranking of these. So here I have these two examples of this pattern. So this is my C with P and Q, Q, P. And here's some other imposter that says, hey, I'm the product. You know, I'm called C prime, and I have P prime and Q prime as the two projections. You know? Why do you think this guy is better than me? Right? And it is better if you can show that there is a unique morphism, unique arrow coming from C prime to C. That kind of projects the C prime into C, and it's a unique arrow that fulfills these conditions. So this is called factorization conditions. So like you say, P prime is not really a prime number because it factorizes as M times P, right? And this one is not a prime number because it factorizes M times Q, right? So they both, these, if you're thinking of them as numbers, you know, you would say both these numbers have a common factor called M, except for instead of multiplication, you have composition, right? But it's the same thing. P prime equals P times M. Q prime equals Q times M. We have factorized M out of these guys, okay? So they are not really elementary in the sense because we can pull out a factor out of them. So this guy is better, more pure than these guys. So, of course, if it doesn't always exist, but if it exists and it's unique, then we say this guy is better than this guy. So that forms like a ranking among these things, you know, maybe it's a tree ranking, or maybe there's separate areas or so on, you know. And in these cases, you would not find the best one, but in some cases, the ranking works beautifully and it gives you the best one and it's unique, okay? And in that case, we call it a product. This is a real product. Not every category has products for every pair of objects. That's fine. We are interested in ones that do have this. And again, there is a connection with logic, okay? Because this is sort of the introduction of conjunction. We had the elimination before. Now this condition of factorization corresponds to introduction, right? Because you can say, okay, if A follows from C prime and B follows from C prime, so we have some kind of assumptions, you know, and we can prove A and we can prove B, then A and B is also true, right? And A and B corresponds to this object C, right? Because that's a formula, and this is an object. A follows from C prime, well, that's our P prime, right? A follows from C prime. That means there is a morphism here. B follows from C prime. There is a morphism Q prime that proves it, right? So if these two things are true, then A and B follows from C prime, right? A and B follows from C prime, from these assumptions. C prime are our assumptions. And that's proven by M, right? C follows from C prime. That's the morphism M, okay? And then going deeper into this is, okay, but what does it mean that this is a unique morphism, right? All right? Because this just shows that this decomposition works, but what about uniqueness? And uniqueness of this morphism translated into proof theory is exactly the expression of the thing that Phil mentioned, that introduction and elimination are the opposites of each other. So if you eliminate and then reconstruct, you get the same product. And it's one of the Gensen's principles in proof theory, that they are the opposite, right? Elimination followed by introduction will give you back the same thing. So I'm not gonna go into details of this, but just to show you that there's like really one-to-one correspondence between category theory and logic, and of course programming. So here's another universal construction. This is the last one, so bear with me. This is the construction of function object, okay? Because what are functions really in Haskell, right? What's the type function? That's not really morphism, right? Morphism is not an object. A set of morphisms between two objects sort of corresponds to type from A to B, a function from A to B, right? But a set of morphisms is not an object, it's a set. It's like outside of the category. It's called a home set, by the way, right? It's a set of morphisms between two objects. But is there an object in the category that corresponds to the set of morphisms? If there is one, it's called the function object, okay? So in order to define a function object, which in Haskell is this A arrow B, that's a function object. That's a type, which is an object, right? You have to have first products. Function object can be constructed only if you have products in your category, which you don't always have, but in Haskell you do, right? So this is the function object. It's an object. I call it A to B. That's maybe a notation more closer to logic than what we use in Haskell, but you know, you take a product of these two. So think of, you know, sort of like Cartesian product pair. Okay, pairs. You take a pair of function A to B and an argument of type A. Okay? What can you do with this? You can apply this function to this argument and you get something of type B, which is an object B. So this morphism here called eval, it just evaluates a function on an argument, right? So this is the pattern. This is the pattern that we are looking at. And the universal construction is that what we call a function object is really the best one. So like if there is any other one that says, oh no, I'm a function object, no, okay? If there is an object Z and you make a cross product with A, you know, and there is a sort of a pretend eval here, then you can find a unique function H, unique morphism H, that factorizes this triangle. Okay? I won't go into details. It's kind of boring stuff. And, well, you can find it in my blog, described in more detail. And now this pattern it corresponds in logic to modus ponens, right? The basic idea in proof theory, you know, that if it's true that B follows from A, and if it's true that A and, you know, this and this, then B must be true. No? If you can prove B from A and you know that A is true, then B is true. So modus ponens corresponds to this universal construction. Okay, and in fact, from the same diagram, you get what in Haskell we call currying. So that you can think of this as a function. Because this is a product, you can think of it as a function of two arguments, right? What's a function of two arguments? A function of two arguments is really a function that takes a pair, right? So a product. So a function from product to B corresponds through this H to an application of function from A to B to A, which means give me an A and I'll give you a function from A to B, okay, which is currying. That this is just a side thing. Okay, now the negation. So there is one more operator that takes a proposition A and gives you the negation of this proposition, not A. So if A is true, then not A is false, and vice versa, right? So now we don't need a special construction for this. In category theory, it corresponds to saying that there is an arrow morphism from A to void. Okay? Now, why is this negation? Okay? So if A is true, then A to void must be false. Okay? What does it mean that A is true? It means that type A is inhabited, right? It has elements. So if A is inhabited, then actually there are elements of A, and if I have a function from A to void, I would be able to create void from nothing. Which kind of sounds interesting. But you're not supposed to be able to create an element of void, right? Because void is an empty set, corresponds to an empty set. It has no elements. If you give me a function like this, and there is an object, there is an element of A, I can just apply this function to A, and bam, I get an element of an empty set. That's not possible, right? So if A is inhabited, A to void must be impossible. So A to void, this function type, is not inhabited in this case. Cannot be inhabited. There cannot be a function like this because everything would explode, right? And vice versa, if A is not inhabited, which means, in our case, it means false, right? So if it's not inhabited, it's just void. It corresponds to void, right? Is there a function from void to void? Yes. It's one of these crazy functions, you know. You'll never call it because you cannot provide an argument for it, right? But it exists. It's the identity on void, you know. It maps an empty set to an empty set. That's fine. Mapping an empty set to an empty set is okay. So this is why it's called negation. Negation is actually a function object in a category. So combining all these three things together, okay, we get a category that's called Cartesian closed. It has all the products, that's why it's called Cartesian, right? It has all function objects, so for any two types, there is a function object that corresponds to morphisms between the two types. Sometimes it's called an exponential, and that's the meaning of closed, having all function objects, and has a terminal object. Okay, these three things. If it has these three things, and not every category does, but if it has these things, it's called Cartesian closed category. And you can think of the terminal object, empty tuple. It's like the zeroth power of some type, right? So it's like you can say it has all infinite products as well, and as nullary products with zero elements. So finally, this is the extension of the Curry-Howard isomorphism. It's called Curry-Howard-Lambek isomorphism between these three branches of mathematics. And the part that Lambek came up with is that Cartesian closed categories are a model for the simply typed lambda calculus. So simply lambda calculus, we already know is a model for logic. Now it's also now it also has a model in Cartesian closed categories, right? And objects are types, morphisms are terms in logic, in programming, right? And there's also the environment thing that corresponds to a product of these judgments about variables in our lambda calculus. Okay? And now let's go a little bit to the side and consider different kinds of logic, like two major types of logic. One is the classical logic that we've always known from ancient Greece and so on. It's the classical logic, which is kind of very strict and says that every statement or every proposition is either true or false, right? This is what Hilbert was trying to prove, that every proposition is either true or false, and we eventually find a proof for this. And then Gödel came and said, no, you know, there are some statements that are neither false or true, right? So this led to this intuitionistic logic in which a statement can be true, a statement can be false, or you can just say, well, what does it mean is, right? If you want to avoid the answer to the question, you say, well, define is, right? So intuitionistic logic, if we want to describe it better, it's a logic in which there is no law of excluded middle. Law of excluded middle means that A or not A is true. Because either A is true or not A is true, right? Well, in intuitionistic logic, it doesn't work. Because A may be from this gray area, and you know, there is a negation of this thing, and there's this thing, and we don't know if this is true, the or of these two things is true. Now, or corresponds to this sum type, right? And it simply means that when we look at the lambda calculus, this is not provable in the lambda calculus, okay? So law of excluded middle has no translation, cannot be derived in lambda calculus. There is no function that will produce this. Other way of saying the same thing, no lem, is that we cannot eliminate double negation. Right? Because double negation is not A. Well, not A is the same as A, right? In classical logic. Not in intuitionistic logic. So not A, now going to Lambek, right, would be translated as a function that takes not A, which is a function from A to void, and returns void, right? So it's double negation. First we negate A, that's a function from A to void, and then we pass it to negation, which is a function from this thing to void, right? And this is something that's not true in lambda calculus. Okay, it's not the same as A. We kind of think of this as A because, you know, if there is A, you know, then if you give me a function from A to void, I will apply this function, I'll get a void, so I can return this void that you gave me, an element of void, right? Well, we can't. So the Curry-Howard part of the isomorphism says really the lambda calculus is equivalent to not classical logic, but to intuitionistic logic. You cannot prove the law of excluded middle using lambda calculus or double negation. You cannot prove double negation, right? So this is a subset. So you might think, okay, so we cannot do classical logic. This is very limiting, right? So we programmers are not supposed to do this, right? So is there something that we can do with classical logic? And turns out, yes. The logicians came up with this before programming, right? Gödel and Gentzen. They came up with this idea that, lo and behold, you can take classical logic and embed it into intuitionistic logic. Which means if you have a proposition in classical logic that is provable, you can translate it into some other proposition in intuitionistic logic, and you can translate the proof into an intuitionistic proof that does not use double negation, does not use law of excluded middle, and you will get something, right? So there is a correspondence between propositions. It doesn't mean that if you get a proposition from classical logic and you just put it inside intuitionistic logic that you can prove it. You might not be able to do this. But if you transform it, put it here, the transformed thing can be proven, always, and vice versa. So there is a one-to-one correspondence. And the trick to do this is really, really simple. So you take a proposition from classical logic and you say, okay, I'm going to invert everything inside there so that I apply double negation to all my assumptions, right? So the transformation is really, I'll do the double negation. I get a new theorem, right? And this new theorem can be actually, you can apply intuitionistic logic to it, and you prove something, and if you apply double negation to it, you get back the result of this first theorem. So every theorem can be translated using double negation into a theorem, and if you can prove it in the intuitionistic logic, then you can do the double twist here, come back to here, and you have a proof of the original thing in classical logic. So what does it mean to us? Well, it means continuations, okay? So double negation looks like this. You know, the A to void goes to void. It can be generalized to A to R. For every R, A to R goes to R. And of course, if this is true, then you can substitute void for R and you get it. But this is just continuation passing, right? A to R is the continuation, a function that handles A, right? Give me a handler. I'm not giving you A back. I don't know how to. But I can, if you give me a handler, I will call it with A. Okay? That's the idea of continuation passing, right? So if you extend lambda calculus with these continuation passing things, or if you think of transforming a whole program to continuation passing style, you do the CPS, right, on a program, which means the same as double negation. You know, then you get another program that actually runs. So we have a way of embedding classical logic into programming, but we have to do this CPS transform. And finally, this is the last slide. No, this is one before last. And I'm not going to explain this because this is like higher category theory. It's called Ioneda's lemma. But I want to show you that this continuation passing style actually follows also in category theory from like the most, I think this is like one of the most important theorems in category theory that category theorists invented, right, is the Ioneda's lemma. And Ioneda's lemma tells you exactly this thing that, you know, introduces continuation passing style in a categorical way. It says that if you give me a function from a to x, and this identity functor here, that takes a continuation and returns x, then it's equivalent to a, this type, right? So that's the Oneda's lemma, and corresponding to continuation passing style in category theory. So here's the conclusions, okay? It's all the same. All these three theories are identical. It's just different notation for the same stuff. You know, you have type theory in lambda calculus, and the other part of this Cartesian closed categories. It's the same as logic, okay? And because of this, there is a lot of cross-pollination. Mostly nowadays, you know, we've done already this cross-pollination from logic into programming, right? That's something that Phil explained. But there is also cross-pollination between category theory and programming. It's like, this is something Edward Kmet would talk about, if he was invited here, and if he came here. And finally, you might ask yourself the question: is like, if these things are the same, maybe there is like a grand unified theory behind this, and mathematicians would love to have something like this grand unified theory. And one attempt at this is the homotopy type theory, which is very hot right now. A lot of mathematicians are working on it. So the idea is maybe something will come out of this, or maybe not. We don't know. Okay? Thank you.